Hello, everyone. Today we're going to be looking at the gas laws that we discussed in class. We're going to focus mainly on what I called the combined gas law. But remember that there were three different relationships that led up to that combined gas law. So if you'll remember from class, we have that pressure and volume are inversely relational. So we've got if you have a pressure and a volume initial and you change them, they're going to be equal in this relationship. The relationship also exists directly proportional between pressure and temperature. Again, if you have your initial and you change one of them, the other one is going to change. And then we also have the relationship between volume and temperature that mathematically looks like this. And then in class, I showed you how all three of these can be combined together to solve problems. And the main equation that I'm going to have you focus on for this section is what we call the combined gas law. And it just says that if I have a gas at an initial pressure, volume, and temperature, and I change it in any way, I can predict what the other is going to be. So now, when you look at the problems we're going to tackle here in this demonstration, you could remember all four of these equations and you could decide which one to use on any given problem. However, I'm going to show you how to use only this one equation for all problems, no matter what variable they give you, because I believe in you memorizing as little as possible and using it to its greatest advantage. So let's look at our first problem. Okay, so let's have an attempt at trying one of these problems with these calculations. First, let's read our problem, and we're going to highlight the data that it gives us. A diver blows a 0.75 liter air bubble 10 meters under the water. As it rises, the pressure goes from 2.25 atmospheres to 1.03 atmospheres. What will be the volume of the bubble at the surface? Okay, so let's remember what our combined gas law says. And remember, we are going to show that we can use this combined gas law for all problems relating to the comparisons of gases. So this just says that the initial pressure and the initial volume over the initial temperature is equal to the second pressure times the second volume over the second temperature. And as a reminder, temperature must be in Kelvin. We'll talk about that later in future problems. So what did they give us here to work with? Well, this 0.75 is our initial volume, not pressure, initial volume. The 10 meters is just extra information. Meters is a distance. It doesn't even apply to gas problems, so we can just cross that out. This 2.25 atmospheres here, that's our initial pressure because it says the pressure goes from this to this pressure here. So this is our second pressure. And what will be the volume? So they're asking us to solve our second volume. Now, did they give us any information regarding temperature? If you said no, you're correct. When they don't give you any information about one of the variables, you can assume that variable stays constant and you can let it be equal to 1. That's okay. So we're going to head and filling in our formula with these values that we see in our problem. So our P1 is going to be 2.25 times our volume 1, which is 0.75, all over 1, which is our first temperature. So I'm not going to write that because if you divide by 1, you just have the same thing, equals our second pressure, which is 1.03, times our second volume, which is what we're trying to solve. So we're going to just let that be its variable. So when you go to solve this, you are just using algebra. So to get V by itself, we're going to divide by 1.03 on both sides. Here it cancels out and becomes a giant 1, so we're left with V2, which is what we're trying to solve. And then we go to our calculator and plug in 2.25 times 0.75 divided by 1.03, and we get 1.6383. So now we got to look at significant digits, right? You will see that our lowest number of significant digits is right here in our 0.75 liters. So that means that we have to have 2 significant digits. So our answer is going to be 1.6. Now we've got to remember units. And just like the units here for our initial is liters, that is the units for volume. And that would be your answer. Okay, we're going to look at another problem with other variables comparing gases. Let's go ahead and read it and highlight our data. A helium balloon in a closed car occupies a volume of 2.23 liters at 40 degrees Celsius. If the car is parked on a hot day and the temperature rises to 75 degrees Celsius, what is the new volume of the balloon? Okay, let's identify what they gave us now. Well, they gave us an initial volume and an initial temperature, and then they gave us a second temperature, and they asked us to find a new volume. Let's write out the combined gas law. P1V1 over T1 equals P2V2 over T2. And let's ask ourselves, which one of these variables did they not mention at all? Well, if you said pressure, you're correct. So that means we're going to let pressure equal 1. Because it equals 1, 1 times volume is just going to be the volume. So I'm just going to write the volume down. Our initial volume then is 2.23 liters over our initial temperature, which is 40 degrees Celsius. Now here's the issue with this. Temperature must convert to Kelvin. You must convert your temperatures to Kelvin all the time before you can use them in the formula. So let's go ahead and do that with both of our temperatures right now. 40 degrees Celsius plus 273 is going to equal 313 Kelvin. 75 degrees Celsius plus 273 is going to equal 348 Kelvin. So these would be the values you would use as your T's. So our initial temperature then is 313 Kelvin equals our new volume, which is what we're trying to solve, over our second temperature, 75 degrees C is what they gave us. We converted it to Kelvin, 348 Kelvin. Now, again, just straight algebra to solve for your variable. we're going to multiply both sides by 348. When we do this, this becomes a giant 1. 1 times V is just the volume you're trying to solve. You'll plug into your calculator 348 times 2.23 divided by 313, and you get 2.479. Well, now we have to look at significant digits. Our lowest significant digit is going to be right here at 2 significant digits. So our answer would need to be 2.5. We've got to look at what is the units for volume. It is liters. So we got to make sure we have that included. 2.5 liters would be the new volume. And this makes sense. As you increase the temperature, you would expect the volume to increase because it's directly proportional. I hope you're starting to get the hang of this and seeing how we use that combined gas law for every problem we come in contact with. This is the third option of combinations of these variables, and we are going to compare pressure with temperature here. So hopefully you're seeing that if we're going to compare pressure with temperature, we're keeping volume constant. So we're going to let volume equal 1 in this case. Let's go ahead, write out our formula. We've got P1 V1 over T1 equals P2 V2 over T2. And our volume this time will equal 1 because it's constant. And again, because 1 times pressure is just the pressure value, I don't have to write it in there. Let's read our problem and highlight the data. The pressure of the oxygen gas inside a canister is 5 atmospheres at 25 degrees Celsius. And the canister is in a new location where the temperature drops to -10 degrees Celsius. All right, let's identify what we've got. Here is our initial pressure and our initial temperature. -10 degrees is our second temperature. And they're asking us to find our new pressure. So, again, because we're dealing with temperature, our temperature must be converted to Kelvin. So let's go ahead and do that. 25 degrees plus 273 equals 298 Kelvin. And -10 plus 273 equals a 263 Kelvin. We fill this into our equation. Our P1 is 5 atmospheres over our temperature of 298. That's supposed to be an 8. Equals our second pressure that we're trying to solve over our second temperature, which is 263. Algebra tells us to solve this problem. We multiply both sides by 263. This becomes a giant 1. We're left with our pressure here. 263 times 5 divided by 298 equals 4.413. Now we have to look at significant digits. Our significant digits for all of our numbers is 3. So our pressure is going to equal 4.41. But now we have to look at units. Our units for pressure in this problem are atmospheres. So atmospheres is our units. Our last problem in this series is going to be one where we actually look at all three variables of gases combined all at once. So you're going to see pressure, volume, and temperature discussed here. In a situation like this, you would have no choice but to use the combined gas law, where the other ones, when you're only relating two variables, you can think of the combined gas law or you can think of the individual gas laws. But in this problem, you must use the combined gas law completely in its fullest. And again, that's because all three variables are discussed. Let's read the problem and see that. A gas at 110 kilopascals, that's a unit of pressure. Remember, just like atmospheres or torr or millimeters of mercury, kilopascals is a unit of pressure. So a gas at 110 kilopascals at 30 degrees Celsius fills a flexible container with an initial volume of 2.00 liters. If the temperature is raised to 800 degrees Celsius and the pressure increases to 440 kilopascals, what is the new volume? Well, let's identify each of these values. So like we said, kilopascals, that's our initial pressure. 30 degrees Celsius is our initial temperature. And the volume that applies with that, our initial volume, is 2 liters. If the temperature is raised to 80 degrees Celsius, that tells us that's our second temperature. And the pressure is increased to 440 kilopascals, that's our second pressure. What is the new volume? That's what they're asking us for. Okay? Remember, this equation looks like this. P1 V1 over T1 equals P2 V2 over T2. My 1 there looks a little awkward. Let's fix that. There we go. So now we just have to convert our temperature to Kelvin. Always, always, always. We've talked about all of the variables, so nothing is constant, so we don't get to choose one of them that's equal to 1. We have to fill them all in, and then we calculate. So first, let's convert to Kelvin. We've got 30 degrees plus 273 equals 303 Kelvin. And then we've got 80 degrees Celsius plus 273. This equals 353 degrees Kelvin. Those are going to be our temperatures that we use. And now we can fill in our formula. P1 is 110 kilopascals. Our V1 is 2 liters. Our T1 is 303 Kelvin. This equals our P2 of 440, our V2, which is what we're trying to find, and our T2, which is 353 Kelvin. All right. So our algebra says that first we need to multiply, you can think of it by 353 from both sides. That would cancel this and that out, and we'd get 440 V2 equals whatever this is going to equal. So let's multiply it out. 353 times 110 times 2 divided by 303 equals 256.3. And then we divide by 440. Again, this cancels out in this giant 1. So we've got our volume equals 0.5825. Now we have to look at significant digits. Let's pretend that I had written this as 30.0. I should have caught that when I was typing it. If I had written that as 30.0, our lowest significant digits would have been right here with our pressures at 2 significant digits. And so our answer would need to be written as 0.58. Okay, so that'll do it for this demo. I hope that shows you how you can use the combined gas law no matter what situation of comparing gases that you're in. I hope you guys have a great day, and I will see you later. Bye.